In this chapter, we're going to talk about radical reactions, and so this first video is an introduction to radicals. So radicals, or free radicals, are formed when bonds break homolytically. And what makes a radical is these unpaired electrons. Molecules don't like to have unpaired electrons, and so radicals are very reactive. Now, when we draw mechanisms involving radicals throughout this chapter, notice the difference between the regular arrows that we use when we're showing the motion of a pair of electrons. We use the regular double-headed arrow. When we draw reactions involving the movement of just a single electron, we use these sort of half-hook or fish-hook arrows. The structure of the radicals determines a lot of the properties of the reactions we're going to look at, and radicals tend to be trigonal planar. In some cases, they may be sort of almost planar. They call it a shallow pyramid, and being sort of sp3 hybridization-like, but it sort of flops back and forth between these two different configurations where the bonds are sort of pointing down a little bit or the bonds are sort of pointing up a little bit. But this is close enough to planar that we can generally just think about the radicals as being trigonal planar and sp2 hybridized. So radicals are neutral. They don't have a positive or negative charge, but they're still electron deficient because they don't have a complete octet. And so radicals follow the same stability trend that we saw in carbocations, right? So methyl are the least stabilized, and as I go to primary, secondary, and tertiary radicals, they get more stable. And also like carbocations, radicals are stabilized by resonance delocalization. And so if I have my unpaired electron in an allylic position, I can draw a resonance structure where I move the lone pair over to this other carbon. And so by spreading out that unpaired electron, I can increase stability. And so allylic radicals are particularly stable, and benzylic radicals, where I have the radical sort of one carbon off of the benzene ring, because I can draw lots of different resonance structures and spread out that unpaired electron throughout the entire benzene ring. That makes benzylic radicals even more stable than allylic radicals. It's just sort of putting all of this together in terms of stability. So benzylic radicals are the most stable, then allylic, then tertiary, then secondary, then primary, then methyl. So most stable, least stable. And also, like carbocations, we don't like to have a positive charge in a vinylic position, so the positive charge is on one of the carbons that are connected by the double bond. Similarly, we don't like vinylic radicals. These are particularly unstable. So one thing that's related to radicals is the strength of carbon-hydrogen bonds. And so bond strength is inversely proportional to the stability of the radical that we would form by doing a homolytic bond cleavage. So if I try to break this CH bond and do it homolytically, where I split up the electrons and one electron goes to the carbon and one electron goes to the hydrogen, because the methyl radical is particularly unstable, that requires the most energy. And then as I go to, right, if I break this CH bond, I'd be forming a primary radical, and so that bond strength is a little bit less. It's easier to pull that hydrogen off. And then, in this case, this CH bond is the weakest because it would create a tertiary radical, which would be more stable than the radicals we'd form from these other bond breakings. When we first learned about reaction mechanisms, we memorized a couple patterns. We had nucleophilic attack, loss of a leaving group, etc. Well, similarly, there are some common patterns in radical mechanisms. Now, I'm going to show you all the patterns, but I don't think you need to have these memorized. But you do need to be able to draw the curved arrows if you're given a step in a radical mechanism. And also, we'll be learning some radical mechanisms that you'll need to know. So the first pattern is homolytic cleavage, right? And that's just where we're breaking a bond and we split the electrons equally between the two atoms that were bonded. And I should have mentioned this on an earlier slide, but I guess it's okay to mention it now. Typically the way we do this is with heat or by absorbing a photon, so by using high energy electromagnetic radiation. And so oftentimes the way we'll represent that is the delta symbol represents heat, and then right? The energy of a photon is equal to h nu, and so oftentimes when we're achieving homolytic bond cleavage by using high energy light, we'll write h nu to represent the photon that that bond or that molecule is absorbing. All right, the second pattern we have is addition to a pi bond. And again, notice in all of these cases we're using these fishhook arrows when one electron movement is involved. We also have hydrogen abstraction, which is not the same as proton transfer, because proton transfer is a two-electron process, often resulting in the creation or destruction of ions. In hydrogen abstraction, right, this involves radicals. And we have both a radical in the reactants and the products. Halogen abstraction is very similar to hydrogen abstraction. And then we also have elimination, which is the reverse of addition to a pi bond that we saw on the last slide. And then coupling involves the destruction of our radicals. So if we have two radical species that come together and form a bond, then we went from having radicals to having no radicals. When we talk about mechanisms involving radicals, we often class the steps in those mechanisms into three different groups. So we have initiation, termination, and propagation. And so the first one, initiation, is a step where radical species are formed from non-radical species. And so homolytic bond cleavage is an example of that. Right, I started without having any radicals, and when I cleave that bond homolytically, I end up with radicals. Propagation steps occur when radicals react with non-radicals and new radicals are formed in the process, right? So the net is no change in the number of radicals. So addition to a pi bond, right, I have a radical in the reactants, I have a radical in the products. Hydrogen abstraction, again, radical in the reactants and a different radical in the products. And so they're called propagation steps because I still have radicals that can go on to react with other things. And then the last category, termination steps, occur when two radical species react to form a non-radical, right? And so this gets rid of radicals and sort of ends this chain of radical reactions. And so coupling is an example of a termination step.